measures of variation, and we are going to talk about understanding and interpreting them. There is an equation that's associated with standard deviation. I'm going to show you how to calculate it by hand with a very small data set, and I'm going to show you how to calculate it on StatCrunch. I am going to ask that you do it once by hand, and then I'm also going to ask that most of the time you're going to use StatCrunch because it just takes less time. There's fewer places to make a mistake. But it's important that you do at least one hand calculation so you understand the formula. So now when we talk about measures of variation, the easiest one to calculate is the range. And the range is simply the difference between the maximum and the minimum values. It's just the distance between those two. It's very sensitive to extreme values. It's not as useful as other measures of variation, but there it is. So the range and the midpoint kind of go together. They're easy to calculate, but we don't use them very often. Again, we're going to carry our calculated value one more decimal place than the original set of data. When you are doing a series of calculations by hand, it's very important that you do not round in the middle of your calculation. Very important. So let's do the standard deviation. The standard deviation for a sample is denoted by a lowercase s. So this tells us the average distance of the data points from the mean. So when we get done calculating a standard deviation, it really does talk to us about how the data vary. On average, the points are this value from the mean. If the standard deviation is small, we know that the data are clustered close to the mean. If the standard deviation is relatively large, then we know the data are quite spread out. Here is the formula. Now, order of operations is very, very important. So remember, we're going to go to the innermost calculation first. So the first thing you do is you take each individual score and subtract it from the mean. Once you do that for all your data points, then you're going to square each data point. Once you square them, then you add those all up. You're going to divide that sum by the number in the sample minus 1. And lastly, you're going to take the square root of that calculation. Now, one of the things that happens is we talk about these are measures of variation, and one of the measures of variation is variance. Variance is simply the square of the standard deviation. So variance is going to be s squared, and then we just would not take the square root of that. We do not use variance very often because it's very hard to interpret. The variation is much easier to interpret. Here is the Archaeopteryx data, and we will look at this and do a hand calculation of the standard deviation of the femur, and then we are going to do the calculation of the standard deviation, both the femur and the humerus, in StatCrunch.
So we are going to do the Archaeopteryx standard deviation mean by hand, and I just want to show you, remember the formula for the mean is the sum of all the individual data divided by the number of the data. So if we look at the Archaeopteryx, we are going to, and I'm just going to do the femur, we're going to do 38 plus 56 plus 59 plus 64 plus 74, and we're going to add all those up and we're going to divide by 5. So that's going to be 291 divided by 5, which comes out to 58.2. Now remember, this does have units. That would be 58.2 centimeters. Remember, rule of thumb is to take your calculated number, your statistic, out one place value further than your original data. Our data was to the nearest 1, so we'll round our mean to the nearest tenth, and this does come out exactly even. So we know that the mean length of the Archaeopteryx femur is going to be 58.2 centimeters. Oops, I didn't mean to put it there. 58.2 centimeters. Now let's go ahead and do the standard deviation. Now remember, the formula for the standard deviation is that S, and we use a lowercase s to stand for the sample standard deviation, and it is going to be the sum of each individual value minus the mean, and then because some of those are positive and some of those are negative, we square it to get rid of the negatives. We're going to divide by n minus 1, and then we take the square root of the whole thing. So let's go ahead and let's set up a table, and I'm going to put my values for my femur. Let's go back up, femur. So I'm going to put my values here, 38, 56, 59, 64, 74. And I'm going to set this up, so this is my x. Now I want to do my individual x minus the mean. Then I'm going to square it. And then I'll finish up. So I'm going to do 38 minus 58.2. I'm going to do 56 minus 58.2. I'm going to do 59 minus 58.2. 64 minus 58.2. And 74 minus 58.2. So now you can see I did those calculations. We have some negative numbers and we have some positive numbers. If you're going to be doing this by hand, you'll want to come up with the sum of this column, and it should always be 0. That's part of the reason why in the next step we have to square everything, because otherwise the number of 0 doesn't give us any information. So now I'm going to square those 5 differences. So now I've squared them, and by squaring them I've eliminated any negative signs. And do not round at this. We just take it as it is, and when I add this up, this comes out to be 696.80. Now, go back to my formula. The next thing I'm going to do is divide by n minus 1. So I'm going to take 696.80 divided by, I have 5 individuals minus 1. I'm going to divide it by 4. And when I do that, I get 174.2, and then I want to take the square root of everything. And I get 13.198, and it goes on and on and on. Now this is the place where I go back to my original data. It was ones, so I'm going to take it to the nearest tenth, so it would round to 13.2, and my units on my standard deviation is the same as the units of my data, so it'd be 13.2 centimeters. That's going to be the standard deviation of my femur for this Archaeopteryx. As you can see, doing it by hand is tedious, but it does give you a feel for the formula. So I would recommend you do small data set, a small data set or two by hand, because that's going to be important to help you understand the definition of standard deviation.
We're going to use StatCrunch to help us calculate the mean and the standard deviation for the Archaeopteryx data that is on slide 37 in the PowerPoint presentation. You can rename your variables just by going up to the top and typing over it. So I'm going to do my femur first, and then I'm going to do my humerus. Oops, better spell it right. And then I'm simply going to type in my data. Okay, now when you're going to do your calculations, you go up to Stat. I want to start with summary statistics. That's where we find the mean and the standard deviation. And my data is in columns. And I want to select both columns. We might as well do it at the same time. So if you do shift click, you can choose more than one column. And I'm going to double check. It'll tell me the number, the mean, the variance, the standard deviation, the standard error, minimum, maximum, and the quartiles, and does it tell us the median? I was double checking for that. So that's everything we're ever going to need for this. So I'm going to do compute, and there they are. Femur, I have 5 and 5, tells me the mean, the variance. Remember, the standard deviation is the square root of the variance. What does the standard deviation tell me about this data? It says on average the femurs were closer to the mean than the humerus bones. And so on average that's going to be 15.9. On average the femur will be 13.2. And remember, we take our statistical numbers and we take them one place value more than our data. And so since our data was to the nearest 1, we're going to take the numbers that were in those. The standard deviation is a measure of the variance. So in other words, the standard deviation is also a non-resistant measure because you use the mean to calculate it. So since those extreme values affect the mean, they'll also affect the standard deviation. And standard deviation does have units, and the units are the same as the original units of the data set. When you have sample means that are approximately the same, then it's good to look and compare the standard deviations. We really aren't going to use standard deviations to judge the difference between samples. We basically use the standard deviations to describe our one set. When we use when we're going to compare the variation with different means, we're going to use the coefficient of variation, which we're going to talk about later. but the coefficient of variation is, and I want to, it is your standard deviation divided by the mean. And so you look at a percentage, what is the standard deviation compared to the mean, and you look at it as a percent. When you talk about the population standard deviation, the formula is similar. We're going to take our individual scores, we're going to minus the population mean. We're going to square that difference to get rid of any negative numbers, and we're going to add them up. And then we divide by the number in the population. The biggest difference between the population standard deviation and the sample standard deviation is in the population standard deviation, we don't subtract 1. Chances of you calculating this are slim to none. Now, the variance is equal to the square of the standard deviation. So the sample variance is the formula for sample standard deviation. We just don't take the square root of it. The population variance is the formula is the same as sigma, which is a lowercase Greek letter sigma, so this little thing that looks like a old-fashioned bomb with a fuse, that is a sigma. So sigma is standard deviation, sigma square is the variance. So again, you just don't take the square root of it to find the value for the variance. Now, what we're doing in statistics is we are trying to estimate the parameter using a statistic. And these calculations that we've talked about, we're looking at unbiased estimators. So we use the sample variance or the sample standard deviation to estimate the population variance or the population standard deviation. So what happens is when we use an unbiased estimator, they tend to target the value that we're interested in. A biased estimator would systematically over or underestimate the value that we're interested in. So when we talk about S, estimating sigma, sample standard deviation is an unbiased estimator of population standard deviation. So again, here we have S has to do with the sample, the standard deviation, and then squared is the sample variance. Sigma stands for the population standard deviation. Sigma squared is the population variance. Now range is, remember, was the top and the bottom. The difference between the top and the bottom. And we're going to talk about normal distributions in chapter 4 or 5. And chapter 5, I believe. And we're going to talk about this a little more. But when we talk about normal distributions, most of the individuals lie within 2 standard deviations of the mean. In fact, 95% of the individuals in a data set usually lie within 2 standard deviations of the mean. Now, usual. Usual means most of the time. And so we can use the range rule of thumb to give us rough estimates of usual, because as we go forward, we're going to see, is our value that we got from our calculations, is it usual or unusual? And remember in class we talked about the difference between statistically significant and statistically insignificant. When things are statistically significant, they are unusual if the mean that we assumed was true is actually true. So the minimum usual value is going to be the mean minus 2 standard deviations. The maximum usual value will be the mean plus 2 standard deviation units. When you don't need to calculate the standard deviation, you can take the range and divide it by 4, and you will be in the right ballpark. So if we look at the range, the difference between the maximum and minimum values divided by 4, we will get a very rough estimate of the standard deviation. Good enough to decide what's usual and unusual. Okay, again, standard deviation measures the variation among the data values. When data values are close together, you'll have a very small standard deviation. But when the values if the standard deviation is larger, you will have much more variation in the values. And again, standard deviation does have units, and it's the same units as the original data set. For many data sets, unusual means it is either 2 standard deviation units above the mean or 2 standard deviation units below the mean, and only compare standard deviations if they use the same scale in units and their means are approximately the same. Now, this is talking about the usual, unusual. So we're going to talk about an approximately bell-shaped curve, which we will call normal. And here is what is true about a normal distribution. In a normal distribution, 68% of all values fall within 1 standard deviation unit of the mean. That's more than 2/3. 95% of all values fall within 2 standard deviation units of the mean. Almost everybody. And almost everybody, 99.7% of all values fall within 3 standard deviation units of the mean. So here's a picture. So here's our mean in the middle. We go above the mean 1 standard deviation unit, below the mean 1 standard deviation unit, and we have 68% of the individuals in that data set will fall in that. For IQ is a test to measure intelligence, and IQ is designed to have a mean of 100 and a standard deviation of 15. So what this says is 68% of human beings in the United States have an IQ between 85 and 115. Okay. 95% of all individuals have an IQ of between 70 and 130. So that's 100 minus 2 standard deviations, 100 plus 2 standard deviations. And 99.7% of the individuals will have an IQ of between 55 and 145. And then there are those people who are above 145, those people who are below 55. Does that make sense? So I want you to think about that. I am going to put in some examples of that before I let you see this lecture. And here's an example. So this is what I was trying to think about before. So if we look at heights of adult men from ages 18 to 24, and I'm going to tell you that we use these ages because this is college age. And many studies are done on college age people, mainly because they're at the university, they're taking some kind of class, and it's easy to require them to be a subject in an experiment. So that's how we do get an awful lot of data. So this study was performed in the late 70s, and they found that the mean height of adult men 18 to 24 was 70 inches. The standard deviation was 2.8 inches. They did a graph of the data and found that it was bell-shaped and symmetrical. So that means it's a normal distribution. When we have a normal distribution, we use a capital N just to stand for normal. The first number is our mean, and the second number in the parentheses is our standard deviation. So we look at our empirical rule, which is also known as the 68-95-99.7 rule, and we know that 68% of men between 18 and 24 are between 67.2 inches and 72.8 inches. So we know they are between a little more than 5'7" to a little less than 6'1". 95% of the data of the young men will have heights between 64.4 and 75.6. So that's 2 standard deviation units. So that's 5.6 inches higher than the mean, 5.6 inches lower than the mean. So we know that 95% of men 18 to 24 are between 5'4.5" and 6'3.5" approximately. And we know that 99.7% are within 3 standard deviation units. So 3 times 2.8 is 8.4. And so we know that almost all young men between 18 and 24 are going to be between 5'1.5" and 6'6.5". Now you may know people who are young men who are shorter than 5'1" and taller than 6'6", but they're going to be in this 0.3%. And here we have it visual. So again, 68 between these two heights, 68%, 95% between 2 standard deviation units above and below, and 99.7% 2 standard deviation units, 3 standard deviation units above and below. Now, when we calculate standard deviation, why do we use n-1? And I'm going to tell you it just gives us better results. And so in other words, it helps our sample standard deviation be a better estimator of our population standard deviation. And so we will never underestimate our population standard deviation when we use that n-1 in our calculation for our sample standard deviation. And this is the coefficient of variation that we talked about earlier. So remember, if you have samples that have very different means and you want to compare their variation, the better way to do it is to use the coefficient of variation, which is your standard deviation divided by your mean times 100. So in other words, you're looking at what percent is the standard deviation of the value of the mean. So that way you can calculate those percents from population to population, and those are comparable. So what have we done in this section? We've looked at range, we've looked at the standard deviation of a sample and a population, we've looked at variance of a sample and population, and we used the range rule of thumb. We talked about the empirical rule. Sometimes it's called the 68-95-99.7 rule, and we've talked about the coefficient of variation. That's what we have looked at in this section.